Heat. The final boss. Life requires energy. More people require more energy. More energy means more waste heat. More waste heat means higher temperatures. People can only live within a specific temperature range, and solids melt, sublimate, or burn if they get too hot. The human habitat will be climate controlled. It will maintain comfortable human temperatures. The outside will become much hotter than the inside of the habitat, but heat wants to distribute itself evenly. How do we keep the habitat cool? Two methods. The first method is thermal insulation, to reduce the rate that heat enters the habitat. The second method is active cooling of the inside of the habitat using heat pumps. Heat pumps use energy to move heat. They can cool things. But heat pumps also require energy to operate, so we are generating heat to try to get rid of heat, proving the saying that heat is the final boss. Thermal insulation is very effective, and heat pumps with today's technology are very efficient and can operate in a wide range of temperatures. We can consume a lot of energy to support a lot of people and still keep them cool. Even though we can support a lot of people, as we add more energy to the system, managing the heat would eventually reach the limits of current technology and become a bottleneck. Reaching the current limit. This book explains, as simple as possible, the fundamental physical limitations to human population on Earth. This analysis is not a prediction, wish, or policy proposal. If you want to perfectly preserve the natural environment of the Earth without people, then promote a policy of space habitats and colonizing other planets. If you want to share the planet, we can preserve large areas of the Earth and still vastly increase our sustainable population without significant environmental changes, aka geoengineering. There are countless trade-offs we could consider. Never say that Earth can only support 8 billion people. These trade-offs are useless to answer our central question. What is the absolute limit of comfortable human Earth carrying capacity using current technology? To reach the absolute thermodynamic limit, we have to make the surface of the Earth uninhabitable. The human habitats will be comfortable, and we can have indoor zoos and aquariums that preserve various species and ecologies. But the planet overall will be geoengineered to support the maximum number of humans. The appearance and function of the Earth will change substantially to massively increase its thermodynamic carrying capacity to the current technical limit. Outgoing longwave radiation. If the sun constantly delivers energy to the Earth, and that energy turns into heat, why doesn't the Earth just get hotter and hotter? Space is a vacuum. There is no material outside of Earth's atmosphere to conduct the heat to. But how does the heat from the sun reach the Earth in the first place? Solar radiation, light. We can convert that light to electricity, use the electricity, and that becomes waste heat. The waste heat makes the Earth hotter. What happens when something gets hot? It glows. The way that Earth dissipates the heat from the sun is with thermal radiation away from the sun. The sun glows and heats the Earth, and the Earth glows and cools off. But the Earth doesn't look like it is glowing at night. The light that you can see from the sun during the day is in the spectrum of light visible to humans, which you can also see when an object gets red hot or white hot. But before a hot object glows red, it glows in the infrared. It emits light at a wavelength longer than your eyes can see. Long-wave radiation. Invisible infrared radiation is how the Earth cools itself into space, which is the same thing that spacecraft do. Any human-made artificial spacecraft has to control its temperature in space within an acceptable range, or else it will break or melt. Human spacecraft have special radiators that are designed to collect the waste heat from the spacecraft and convert it to infrared radiation that points away from the spacecraft so it doesn't reheat itself. Radiators have special shapes with ridges to increase their surface area and radiate more heat. In order for the spacecraft to maintain the same temperature, the heat produced by the spacecraft has to balance with the outgoing radiation. The amount of heat that a spacecraft radiates is called outgoing longwave radiation, OLR. If a spacecraft is already at its maximum temperature, and the spacecraft wants to use more energy and produce more waste heat, it has to increase the OLR to dissipate the additional waste heat to prevent the spacecraft from melting. You can often use more energy as long as you equally increase the OLR. Eliminate the greenhouse effect. The first step in increasing the thermal budget of the Earth is reducing the greenhouse effect of the atmosphere. The greenhouse gases in the atmosphere trap heat by being transparent to visible light, but they absorb and re-emit OLR, trapping heat in Earth's atmosphere and the ground. We want to reduce or eliminate the greenhouse effect of the atmosphere by reducing greenhouse gases such as water vapor, carbon dioxide, and methane down to almost zero. This will allow us to use much more energy without overheating. The first step in reducing greenhouse gases is reducing atmospheric CO2, and the first step to reducing CO2 is to stop burning fossil fuels. We should replace fossil fuel burning with terrestrial solar and batteries, geothermal and synthetic fuels where needed. The next step is carbon capture to pull the CO2 out of the atmosphere. Permanently storing CO2 gas is difficult, so we should convert the low-density CO2 gas into a dense, stable solid to keep it out of the atmosphere. We want to turn the CO2 gas back into something like the coal that the CO2 came from. To reduce the greenhouse effect as much as possible, we want to pull all of the CO2 out of the atmosphere, which would make plant life impossible outside of the human habitat, as plants need CO2 for photosynthesis. Plants are necessary for animals to survive, and life is the primary source of methane. So if the plants die, so do the animals and the primary sources of carbon dioxide and methane. Methane is not chemically stable in Earth's atmosphere. If we eliminate most of the methane sources, the atmospheric methane will naturally reduce on its own. Water vapor is the final major greenhouse gas. Water vapor reduces OLR, and clouds and rain can disrupt SBSP radio frequency beams. The solution to water vapor is to sequester all of the water outside of the habitats. We can turn water into rock. In fact, it happens every day, both naturally and artificially, and we explore how in the next section. Without greenhouse gases, there is no greenhouse effect, and the Earth will radiate heat with a much higher efficiency. More like artificial spacecraft in space. But how could we sequester all of the carbon dioxide and water? Sequestration. Sequestration of all greenhouse gases first requires stopping burning fossil fuels, replacing them with renewable energy generated from geothermal and terrestrial solar. Applications that are not yet electrified or cannot be electrified can use synthetic fuels, made renewably, turning CO2 to fuel, burning the fuel to return to CO2 and create a sustainable process. The least disruptive way to reduce greenhouse gases is by sequestering carbon dioxide, turning the CO2 back into something like coal, a durable, high-carbon material we can bury. A material like that will remain stable underground and stay out of the atmosphere. One method to do this is to grow grasses such as bamboo, napier grass, or switchgrass, which convert CO2 into woody biomass. Wood is mostly cellulose, which is made from glucose, which is made from CO2 and H2O. It is possible to preserve the wood for a long time if you keep it somewhere without water or oxygen. But the carbon is always vulnerable to decomposition back into CO2 in that form. A more durable form of carbon for long-term storage is called biochar, formed when you heat wood without oxygen in a process called pyrolysis. Biochar is more of a pure carbon material that doesn't easily decompose further, even with water or oxygen, so you can bury biochar and leave it in the ground indefinitely, like coal. Farming bamboo takes no additional energy input beyond sunlight, and making biochar takes modest amounts of energy for pyrolysis, but that simplifies the storage significantly. Where could we put all of this biochar? Fill up the mining pits with it, or bury and cover it. It is a fairly safe and inert material. Sequestering CO2 is the easier challenge. The greater challenge is transforming the oceans into rocks. Water is a potent greenhouse gas, and the Earth has a lot of it. The Earth's surface is 71% covered by ocean. The salty ocean is a chemically aggressive environment. Most materials are eroded or degraded by the ocean over time, which is why even modern boats must receive regular maintenance, such as repairing coatings, in order to survive operating in the ocean. Creating human habitats in the ocean would face a significant challenge if they had to withstand the waves and corrosion. We could separate out all of the salt from the ocean, but where would we keep the salt so that it would never get wet and dissolve back into the water? And the salt isn't the central problem. The greenhouse gas called water vapor is the problem. The way to turn water into rock is to chemically bind the water with certain very common metals, aluminum, calcium, and magnesium, into stable compounds called metal hydroxides. These metals are some of the most common materials in the Earth's crust, and if you keep digging, there are enough of them available to bind with all of the water, transforming all the lakes and oceans into stone. The metal hydroxide components I propose to use are stable up to temperatures above 150 degrees Celsius. It is possible to bind water with iron, the most common element in Earth, but that compound is not stable above 150 C. Metal hydroxides are naturally occurring and sequester water in a natural process that happens every day called weathering. To sequester significant amounts of water quickly, we would need to create and scale up industrial processes for sequestering water. Practically speaking, what would that look like? We would use 3 of the most common metals in the Earth's crust: aluminum, calcium, magnesium. In the entire crust of the Earth, there is 3 to 4 times as much of these metals as we need to bind all of the surface water on Earth. That means we do not need to mine out the entire crust. We need to access most of the metal from the surface down to a depth of about 10 kilometers. Current bulk mining operations reach 4 kilometers depth, but that isn't the technical limit for mining. Drilling for boreholes and oil wells already extend to 12 kilometers. As we dig deeper, the ground gets hotter and hotter, making mining more difficult. Bulk mining at 10 kilometers requires substantial cooling because rocks at that depth are at 300 degrees Celsius or even hotter. Geothermal energy is actually a form of mining and a form of cooling. Sustainable geothermal energy extraction drills geothermal wells and extracts thermal energy at a rate close to the rate that the heat enters the rocks from below. Extraction at the sustainable rate allows us to use the same well to generate energy for a long time. Unsustainable geothermal energy over-extracts heat from the rocks at a rate much faster than the heat from below heats them up, causing the rocks to cool. An over-extracted geothermal well can take hundreds of years to warm up again. We can use over-extractive geothermal energy to cool mineral veins in advance of deep mining. We can reuse the geothermal wells as mining pilot holes to speed up and simplify the extraction. Some ores are practical to extract in bulk, leaving mining shafts that can be refilled with metal hydroxides. Other ores are better extracted using leaching, where acid is used to dissolve and extract just the metal you want, leaving the rest of the material in place. Bulk mining has not been proven at depths of 10 kilometers, but should be technically achievable using active cooling and remote operation. All of these processes, mining, transport, refinement, conversion, storage, are complex and require significant energy, time, materials, and equipment. To complete the process of removing all greenhouse gases, mostly the water, it would take hundreds of years at least, using current technology pushed to its limits. The Earth's surface would become cool and dry, without a cloud in the sky, after all the water is bound in metal hydroxides. Magnesium is especially useful in the form of hydromagnesite, a compound that sequesters both carbon dioxide and water, is stable to 350 degrees Celsius. There is enough magnesium to sequester all of the atmospheric carbon dioxide in hydromagnesite, leaving the remaining water to be bound by magnesium hydroxide. Calcium and water are two of the three components in cement, which is used to make concrete. Silicon is the third component, and silicon is much more abundant than calcium. Concrete requires more energy to produce, but is also more thermally stable than calcium hydroxide. Cement is a more efficient use of calcium to sequester water than calcium hydroxide, and we need a lot of cement to make structures for human use. Using calcium for cement over calcium hydroxide would slightly reduce the amount of mining required to sequester all surface water, and would produce all the cement we need, with excess, for human structures. White and black. Spacecraft often have a white side and a black side. When the spacecraft is receiving sunlight, it turns the white side to face the sun, so the sunlight reflects off the white part of the spacecraft and isn't absorbed to turn into heat. This reduces the effective incoming heat to the spacecraft from the sun. The side of the spacecraft facing away from the sun is often black, because black surfaces can both absorb and emit heat as OLR. The white side reflects the incoming heat away, and the black side emits the heat as OLR away from the spacecraft. Increasing the thermal budget of the Earth. One bottleneck of sustainable human Earth population is heat, thermodynamic. There are a few things we can do to maximize our available thermodynamic budget. Decrease thermal insulation of the Earth, e.g., reduce the greenhouse effect. Decrease incoming solar radiation. Increase OLR. We could decrease incoming solar radiation with a sunshade in space, but the technology for such a project is speculative. Instead, I propose to make the surface of the Earth more reflective, using durable white tiles, and more emissive using durable black tiles. Increase Earth OLR. We already want to sequester greenhouse gases, keeping the atmosphere clear for OLR. We also want to reflect as much solar radiation as possible, so that when looking at the Earth from the position of the sun, the Earth should appear bright white. We simultaneously want the surface of the Earth to be black, because white does not emit OLR as much as black does. We want the day side to look white and the night side to look black. We could make tiles that have a white side and a black side and flip them twice a day, but that would only expose the black tiles half the time, only at night. Instead, imagine a pure black radiator base layer with thin white north-south ridges. During the evening and the morning, the sunlight hits the surface of the Earth at an angle, and the white ridges reflect the sunlight away, preventing almost all absorption of solar radiation. Only during a brief period around midday would the solar radiation reach the radiator layer and get absorbed. This design passively presents a white surface to the sun for almost the entire day, while always emitting OLR to space, a win-win for reducing heat. Heat sources and insulation. There are three sources of heat in this model of Earth. The first is the heat of the Earth itself, from the formation of the Earth and radioactive decay of materials in the Earth. Today, this energy warms the surface of the Earth and eventually radiates to space. The human habitat creates a new problem with dissipating this heat, because we plan to create a habitat that is a 1 kilometer thick spherical shell around the entire Earth, and maintain that shell at a comfortable temperature. To achieve this, we will use thermal insulation below the habitat to block the heat from below, and thermal insulation above the habitat to block the heat from above. The method I recommend to insulate the habitat is thermally insulating concrete, specifically aerogel-enhanced concrete with fiberglass reinforcement. But if we thermally insulate the surface of the Earth, how will the heat from inside the Earth escape? The heat would build up under the habitat. That is why we would need to collect the heat under the habitat, then transmit the heat using heat pipes in insulated channels through the habitat to transmit and emit the heat from above the habitat. This geothermal energy can be used for energy generation and used to boil and distill water for water purification. The second source of heat is solar radiation, sunlight. Almost all sunlight is reflected by the white ridges above the habitat. The reflection works better than today because the scrubbed atmosphere will be much more transparent. The third source of heat is the energy delivered to the Earth by the SBSP constellation. After the energy is used, it becomes waste heat. The design of the habitat ensures that all of the most heat-producing activities happen in the machine layer above the climate-controlled interior of the habitat. The habitat is a thermodynamic sandwich that looks like this: the Sun, outer space, SBSP constellation, clear atmosphere, rectennas, white reflector ridges, black tile radiator layer, machine layer with heat pumps, water pumps, batteries, fans, incinerators, and hot industrial processes. Thermally insulated habitat roof. Human habitat with insulated heat pipes 1 kilometer tall. Thermally insulated foundation. Geothermal heat exchangers. Earth's interior. All of the heat is concentrated and collected above the habitat into the black tile radiator layer. There is still an atmosphere, and it conducts and convects the heat around, above the sealed and insulated habitat. Aerogel-enhanced concrete. The habitat will use aerogel-enhanced concrete as both a structural material and as thermal insulation. I will briefly describe the modern miracle material of aerogel-enhanced concrete. Concrete is structurally strong, heavy, fairly thermally conductive, and is mostly made of random rocks. Aerogel is structurally weak, lightweight, and a thermal insulator. Aerogel is primarily composed of silicon dioxide, aka glass. Fiberglass reinforcement is also made of glass and is used inside the concrete instead of steel reinforcement, aka rebar, to enhance the strength of the concrete without increasing its thermal conductivity. How do you make aerogel-enhanced concrete? Mix standard concrete with aerogel granules at 20 to 50% volume, adding a mesh of fiberglass of 2% volume, achieving the combined properties below. The density in kilograms per cubic meter of standard concrete is 2,500, of aerogel is about 100, and of fiberglass rebar is about 2,000. When combined in aerogel-enhanced concrete, the density is between 1,500 and 2,000. The strength in megapascals of standard concrete is 10 to 30 compressive. Of aerogel, 0.1 to 1 compressive. Of fiberglass rebar, 500 tensile. Combined in aerogel-enhanced concrete, 10 to 20 compressive. The thermal conductivity in watts per meter Kelvin of standard concrete is 1.5, of aerogel granules 0.01 to 0.02, of fiberglass rebar 0.04. Combined in aerogel-enhanced concrete 0.05 to 0.1. The human habitat foundation will be 50 meters thick, composed of aerogel-enhanced concrete, achieving a thermal resistance, R value, of 1000. The habitat roof needs similar insulation but supports less weight and can be 40 meters thick. The thermodynamic limit. Finding the thermodynamic limit is fairly simple. Assuming we can collect almost unlimited SBSP, which will produce a huge amount of waste heat, we can insulate the habitat from high temperatures. We only need to know how much OLR we can emit to determine the maximum outgoing thermal energy. Once we determine the OLR budget, the system is in balance, so the outgoing heat will equal the incoming energy. The incoming energy divided by the energy use per person determines the maximum population due to heat. How do we determine the maximum OLR? The OLR depends on two things: the emission rate per unit area and the total area. The total area is fixed by the size of the Earth, but the emission rate is highly variable. OLR has an amazing property. The OLR increases with temperature. The higher the temperature, the higher the emission rate. But the relationship is not linear. If you double the temperature, you do not just get double the OLR, you get a lot more than that. The power output of OLR goes by the temperature to the fourth power. If you double the temperature, you multiply the OLR by 16. So, the Earth can emit an incredible amount of power at higher temperatures, like the Sun does. But heat pumps are physical devices, made of materials that have a melting point. Heat pumps have a limited range of operating temperatures, so there is a conflict. We want higher temperatures to increase OLR, but heat pumps have a temperature limit. However, the entire heat pump doesn't have to operate in an environment at the highest temperature. Different parts of the heat pump can operate in separate, thermally isolated temperature zones, allowing the hot end of the heat pump to become much hotter than the pumps and seals could tolerate. The maximum operating temperature of the hot end of the heat pumps of today are 200 degrees Celsius. Other parts of the heat pump operate in 150 degrees Celsius, and the cold end can be as cool as 20 degrees Celsius. This means that at the limit of current technology, the surface of the Earth could become as hot as 200 degrees Celsius, and we could still cool the inside of the habitat. But their efficiency is lower at these temperature limits. There are other thermal limitations, such as the maximum temperature of rectennas and the metal hydroxides used to sequester water and CO2. The highest safe temperature for all of these materials and processes appear to be around 150 degrees Celsius currently, which will be our target maximum Earth surface temperature. Interestingly, the temperatures both above and below the habitat will be similar because they will be connected by heat pipes, and the heat from both will be dissipated by the radiator layer. Analysis of the thermodynamic human carrying capacity of the Earth. Incoming solar is 340 watts per square meter. The white ridges reflect 90% of solar energy, absorbing 10%. Earth's surface area is on the order of 10 to the 14th square meters. The total absorbed solar energy is the incoming solar times the absorption rate times Earth's surface area, which is 17 petawatts. The radiator temperature is 150 degrees Celsius, 423 Kelvin. The radiator OLR per square meter is a constant times 423 to the fourth power, which is 1,815 watts per square meter. The radiator area is the Earth's surface area times 4, which is 10 to the 15th square meters. The total OLR is the OLR times the radiator area, which is 3,700 petawatts. The waste heat cap is the OLR minus the absorbed solar, which is 3,700 minus 17, which is 3,686 petawatts. The usable power is the waste heat cap reduced by the losses from Rakhtenna conversion, which is 3,133 petawatts. Dividing the usable power by the power use per person gives us the Earth population limit of heat of 3 quadrillion people. Thermodynamic bottlenecks. The following table reviews several heat bottlenecks we would face along the way to the current thermodynamic limit. I will offer solutions to each problem in principle, but you can reject any solution as impractical or independently conclude that a problem is intractable, making that bottleneck your own absolute limit. These bottlenecks are all related to problems caused by increasing Earth-ground temperatures. Increasing ground temperatures are caused by increasing energy use to support more people. The temperature increases listed in the table are the simple heating caused by increased energy use. They ignore the greenhouse effect because one of the solutions to our heat problems is to eliminate greenhouse gases from our atmosphere. The first two cases are perfectly moderate without geoengineering. They do not substantially increase the surface temperature of the Earth, and can be achieved within the current areas of human habitation or even less for those who are more interested in scenarios with environmental preservation. With zero space-based solar power energy input, the ground temperature is 15 degrees Celsius, and the human population limit is 95 billion from geothermal plus 319 billion from terrestrial solar, for a total of 414 billion people. The bottleneck is zero space-based solar power energy input causes zero additional ground heating, and population is limited by available energy. The solution is to collect additional solar energy and beam it to Earth using space-based solar power. With 0.2 petawatts of space-based solar power, the ground temperature is about 15.1 degrees Celsius. For a population limit of 414 plus 190 billion, for a total of 604 billion. The bottleneck is that space-based solar power energy input is much less than the solar energy input, causing negligible heating over the baseline. And the solution is to continue to collect additional space-based solar power and use active cooling. With 8.42 petawatts of space-based solar power input, the ground temperature would be 19.6 degrees Celsius, with a human population limit of 8 trillion. The bottleneck would be that significant energy input over baseline causes significant heating, and the temperature would rise by double this amount due to the greenhouse effect. The solution would be to sequester greenhouse gases to reduce the greenhouse effect. With 122 petawatts of space-based solar power input, the ground temperature would reach 63.4 degrees Celsius, for a human population limit of 115 trillion. The bottleneck would be that space-based solar power energy input would be about the same as solar energy input, causing massive heating, killing about all surface life, and causing extreme greenhouse effects from water vapor. The solution would be that the greenhouse effect would cause thermal runaway unless countered. Sequester all the CO2 and water to eliminate the greenhouse effect. Finally, with 3,686 petawatts of space-based solar power energy input, the ground temperature would reach 150 degrees Celsius, for a human population limit of 3 quadrillion. The bottleneck would be that this temperature is around the thermal limits of Rakhtennas, heat pumps, and some sequestration materials. And the solution would be that there is no current technical solution. This is the current thermodynamic limit. Conclusion. The human carrying capacity of the Earth is much higher than current popular estimates. The resource requirements per person and the limits can both be improved with technological development, allowing the carrying capacity to rise even higher. There are various reasons to have more or fewer people, but this book describes the current, hard, physical limits. With generous assumptions of resources per person, using only proven technologies and their predictable developments, the current bottleneck is living space, and the current limit of the human carrying capacity of the Earth is 510 trillion people. The end of human carrying capacity of the Earth. Thank you for listening.